I'm grateful to the previous speaker for mentioning the Big Bang versus steady state controversy, because it's that I'm going to talk about. In particular, I knew Ryle and I knew Hoyle both very well, good friends, and I unwittingly played a small part in the controversy itself. So to begin with, let me show you what a standard optical astronomer, and I'm sorry to call my great friend and colleague Richard Ellis standard, but there's nothing standard about Richard, he's good. Here's what he thought were the great discoveries, the big surprises of the 20th century: cosmic expansion, hot Big Bang, dark matter, and cosmic acceleration. And I don't think any of us would argue with any of those, but we might have our other candidates, such as a list like this. But missing from Richard's list, I contend, is the discovery that objects in the universe undergo dramatic cosmic evolution in luminosity or density. It's missing from everybody's list. And this was discovered in 1955. It was discovered by Ryle and Hoyle. And they, oh, I'm missing a slide. That's it. And they wrote, Ryle gave the Halley lecture that year, and Ryle and Hoyle published a 1955 paper in MN, and it said, radio counts can't be interpreted as homogeneous distribution. There's a great increase in density or luminosity of distant sources. You can't explain the results with sources in the galaxy. The minimum radius of the spherical region is comparable with that of the optically observable universe. We think these are due to effects on a cosmic scale, and evolutionary theory might explain them. Radio stars are very rare, and you can't see them with the big telescopes of the day. Now, this is precisely what we believe today. Every word is a summary of current belief, although we've gone on a bit, but nobody would argue with that picture. Here's the citation record for these things. This is the great paper by Ryle and Hoyle, and you'll see that it has a grand total of 16 citations. Great discoveries were announced usually in Halley lectures. Here's the citation index for the citation history for Ryle's lecture. There's 5 citations. It's incredible. And yet, what they described was exactly what we believe about radio galaxies today. Why was it that the citation index was like this? Well, the answer was the notorious source count of the TC survey, the 2C survey. The slope of this integral count was something like minus 2.7. And everybody knew that you needed a slope of minus 1.5 for a static Euclidean universe. And that's this curve here, which doesn't look very much like the data. Well, of course, what was not known is that the majority in 1955 is that of the nearly 2,000 sources, about 80% of them would prove to be rubbish. They didn't exist. What was also not understood at all was Eddington bias and confusion. Now, Eddington bias, here's a paper which I put the whole paper there, so you have plenty of time to read it. Here's Eddington, great popularist of science. He was the Carl Sagan, Patrick Moore of the day. Doesn't look much like a man of the people, does he? But he really was. His word was God for the public. And of course, he was a most brilliant physicist. Eddington limit, all that stuff. Well, here's a little paper he wrote, and it's called The Eddington Bias because of this little paper written in 1913, and it describes a bias, which is not the bias that people usually talk about today or think they're talking about when they say Eddington bias. This is a bias of how the source count tips when you have noise on your observations. And it's a pure and simple mathematical calculation, which astonishes me that people of the brilliance of Ryle and Hoyle did not make, especially Peter Hoyle, who I consider one of the most brilliant people I ever met. I'm very surprised. But anyway, they didn't know about it. And here's a citation, whoops. Here's a citation index, if I can do it, for Eddington's work. Now, that's pretty weird. This is 1954, 2010, and you'll see it rockets upwards. Why? It rockets upwards because the submillimeter astronomers and their submillimeter galaxies discovered this little paper and used it, quoted it, used it to do what they called debiasing their fluxes. That is to say, doing a Bayesian analysis which wound the fluxes of overestimated fluxes, systematically overestimated fluxes, which you get when you have a steep source count. It wound the fluxes back to a better estimate of what they really might be. Little did they know, the submillimeter people, that Dave Jauncey, a fine radio astronomer and good colleague, had done the job for radio astronomers in 1968. And he wrote a paper about how to debias, and the submillimeter astronomers haven't discovered it. And I've only just explained it to them, and they're all apologetic now, and we can look to a big citation index boost for Dave Jauncey. Anyway, the other problem, we've got the Ellington bias dealt with. The other problem was confusion. Now, this is just to illustrate what confusion is. It's a telescope beam which integrates the background, integrates the faint sources into lumps and bumps. Because the density of these sources on the background, of course, is eventually is much, much higher than a single beam can resolve. So as you see from this, if I wind it back again, this is a set of scans which I did with the Parkes 2.7 gigahertz system on the 64 meter. And this is a repeat of those scans over and over again, about an hour's worth each time. And you can see that the features are all real. And this is the background. It's a double integration to the confusion limit, and it is done with a dual beam differencing system, which is why there are negative sources as well as positive. And out of that picture, if these four are real, then you're lucky. This one's probably good. But maybe there's 5 sources showing there, maybe not. But any of the rest of the stuff that you see is rubbish. It's just the background, the lumpy background being integrated up by the finite beam size. So that's what confusion does. And between the two effects, the Eddington bias and the confusion, that these results produced the mess that was the 2C source count. It produced all the false sources which Ryle and Hoyle claimed to be real sources. So that's the source, the double source of the mess. Now, of course, Hoyle seized on this mistake and went after Ryle. He just happened to have a pet theory, which is known as the steady state, which he developed with Bondi and Gold in 1948. And he knew that his theory was right. Being the proud, blunt Yorkshireman that he was, and self-assured, he was absolutely certain steady state was right. He never wavered from that to the end of his life. Now, in principle, Ryle and Hoyle should have had a lot in common, should have been able to work together and produce this together. The theorist and the observationalist should have produced this great result as a crowning achievement of theory plus new type of observation. In practice, despite having all this in common, they, of course, produced the great steady state versus Big Bang rivalry which wrecked Ryle's discovery. Now make no mistake, Ryle's discovery was based on absolutely terrible data, and he was just plain lucky. It could have gone either way with the data that he used, but in fact he was right. These guys had lots in common. They were both radar developers. In fact, Hoyle probably made the greater contribution to radar over Ryle, because he developed a Lloyd's mirror method of detecting the altitude of incoming aircraft with radar, whereas before that, it had not really been understood how to do it. And Hoyle's method approximately was used for decades by navies subsequently. Anyway, they had lots in common, but how did they interact? They fought at every opportunity like cats and dogs. This is, I think, a quote from Jane Gregory's book, but it may be Woody's, and perhaps it is. They had different research philosophies. 1948, they had a first public argument over radio bursts. They were both dead wrong. In 1951, Ryle claimed radio stars were local. Hoyle claimed there was no evidence. And Gold said they might be some kind of strange galaxies like Seyfert's. He was viciously attacked in the meeting. 55, okay, this is the Big Bang versus steady state controversy. Ryle and Hoyle went after each other like mad. After 2C, what happened? Well, there was a big fight. Mills joined and said that Ryle had got it all wrong. The slope was maybe minus 1.65, and therefore was no different from minus 1.5. And I've got to hurry, I'm sorry. Then I entered the fray in 1968 by producing a source count which was at a slope of minus 1.4. And Hoyle seized on this and wrote yet another paper saying, you only needed another 11 sources over the whole sky to vindicate his steady state theory. This slope of minus 1.4 differed from the conventional wisdom of a slope of minus 1.7 and minus 1.8, and in particular it differed from Jim Garra's beautiful 1966 4C count, which is reproduced in schematic form there. I should have mentioned John Bolton at this stage, because he was my supervisor, and I started off this 11-centimeter survey. John Bolton was possibly the most assured person I ever did meet. And here he is as a young man telling Sir Edward Appleton how things stand. So I got this result, and I thought, well, okay, what's right and what's wrong? And I did my first Cosmo calculations, and they were agonizing because I had nobody to guide me. Sandage gave me an idea or two, but then he left Stromlo, and I was finishing up my thesis and writing the stuff up. And I had to plow on and do these Cosmo calculations by myself. But in the end, I was convinced I got it sorted out. And I found that the source count calculations in a steady state or a non-evolving universe look nothing like the observations. Nothing like them whatsoever. They're curved for a start. They have the wrong slope. The initial slope is never 1.5. It's always about minus 1.2. And the same result was found by Rupert Clarke, and Martin Ryle in 1961. But who would believe them? Anyway, I did this sum all over again, innocent graduate student, and I walked into trouble. No uniformly relativistic universe count remotely, in my opinion, resembles the observed count. The magic slope of minus 1.5 is totally irrelevant. So it is my claim that, Tim's giving me lots of time to tell another anecdote or two here. I met Hoyle many times because he was a great friend of John Bolton. So boozy evenings at John Bolton's place were great for really getting to know Fred, and he actually opened up quite a bit. I got to know Martin Ryle when I went to Cambridge from Parkes. And as I left Parkes, and John Bolton said I was doing the right thing by going to the Cavendish, which amazed me considering his past history with the Cavendish. And he said, yes, I'm doing the right thing. But he said, you'll find Ryle, he said, I'm not too sure about his astronomy, but he's a great engineer. When I got to Cambridge, and I was meeting this fire-breathing, difficult character, supposedly, a friendly head poked its way around into my office and said, Jasper, welcome. Would you have a few minutes? Well, I consulted my diary and thought, yes, I do manage to have a few minutes to spare for the Astronomer Royal. And from that point on, we had a great relationship. He was a lovely man. He was marvelously friendly and helpful to me. So that's how I got to know them both. And then, now what I was going to say. Sorry. I was going to say, I'd done these calculations. I had my thesis finished. I came back to Parkes, and I said to John, look, you know, I've done the calculations about steady state and stuff, and I've done them carefully. And here's the result. And he said, no, wait a minute. My news first. I said, what's your news? He said, I've managed to get Fred to agree to be your external examiner. Anyway, so here's my claim that in this list of Richard Ellis's, the cosmic evolution of a population of galaxies, really must be included. I mean, what's a bigger discovery than that? And it took the optical people, or however you wish to describe them, a couple of decades before they came around to realize that evolution had to happen. Modern radio counts look like this, and there is the region over which all the argument about steady state versus Big Bang took place. Galaxy makers have found a use for AGN at last. Why does this skip, Tim? And we now know then why the evolution of radio galaxies looks like star formation evolution, because radio galaxies are essential to stop star formation and produce cosmic downsizing. So we're useful in the end, and there's my conclusions. I'm sorry, Tim.
Oh, no worries. Thank you. Jasper, I'm dying to know what was Martin Ryle's assessment of John Bolton?
Oh, I forgot that into the anecdote. Yeah. Martin Ryle chatted to me for a few minutes and then said, John Bolton, you worked with him. And I said, yes. He said, well, I'm not too sure about his astronomy, but he's a great engineer.
All right, yes.
Jasper, of course, you showed one of the controversies I remember when you showed those first diagrams, of course, they used the integral source counts, which are
Yes.
much harder to understand than the later things that you showed with the differential.
Yes.
And I'm
Yes.
curious I can't remember when somebody pointed this out, that it was much easier to see what was going on when you switched the differential counts from the integral counts.
I think it was sort of a drip effect. Dave Jauncey really started it. I mean, he wrote this Nature paper which said, look, the integral counts are really the worst presentation you can make because cumulative errors, you don't know what the fitting process is because the errors accumulate down the count. You must use a differential source count. Then, of course, radio astronomers, no astronomers like using the differential counts because then the slope's minus 2.5. And it's damn difficult to plot because it just goes up too fast. So, well, it isn't, it's more than 2.5, it's 2.8 or something like that. So people suddenly went over to the relative, I think it was Beverly Wills was probably the first person to do this. Astronomers went over to this relative differential source count in which the numbers in each bin are related to the numbers you would expect if the universe had, if the source count had a slope of minus 1.5. So we can all agree that the minus 1.5 universe is totally devoid of reality. It doesn't fit anything, but it makes a convenient way to normalize the source count so you can plot them in one picture.